involving cylindrical bodies rotating and essentially rolling without slipping. Okay, the spool has a weight of 30 pounds and a radius of gyration of K0 equals 0.45 feet. A cord is wrapped around its inner hub, this one, and the end subjected to a horizontal force of 5 pounds. Determine the spool's angular velocity in 4 seconds starting from rest. Assume the spool rolls without slipping. So the key thing here is find the speed as a function of time. Again, if you see that kind of thing which is asked, then highly recommend using linear impulse or angular impulse. So which of the two principles do we apply? In order to determine that, let's draw a free body diagram first. Okay, so P, the normal force acting upwards, mg acting downwards. Okay, what else? Is that it? Should have friction, right? Because it rolls without slipping. So friction. And let's call this, well, this point is A. Okay, so we are asked to find the angular speed in 4 seconds. And the other key thing is assumes the spool rolls without slipping. So the spool is initially at rest, and then we apply the force P, it starts speeding up. So when it starts speeding up, the velocity, linear velocity will increase, so would the angular speed, right? Now what you're given here is that if it rolls without slipping, it means that the velocity, the linear velocity v, is always omega angular speed times the radius. So as it speeds up, this point A, which is the contact point, is always at zero speed. Okay? In other words, A is always the instantaneous center of motion because point A does not slip at any point of time. So to find the speed, well, we have only two choices: principle of linear impulse and momentum, and angular impulse and momentum. So if you try to apply principle of linear impulse and momentum, since you're given P, I would try to apply it in the x direction. But when I apply principle of linear impulse in the x direction, I would have to do FF, right? Because somewhere in the linear impulse equation there would be P minus FF, and FF is unknown. So if I know FF, I can solve for the angular speed, which means I need to find FF. Can I do something which prevents me from finding FF? So let's go to the principle of angular impulse and ask ourselves, can we avoid finding FF? Well, you could take moment. When you take angular impulse momentum equation, you can take it about any point. Let's call this point G. If you take the angular impulse and momentum about point G, then FF will appear in the equation because FF applies a moment about G. However, if you apply the principle of angular impulse and momentum about point A, then N, FF, mg all pass through A, and the contribution due to those three forces is 0. The only force which will contribute would be P, and we know P, it's 5 lb. So in this case, it's fastest if you apply principle of angular impulse and momentum above point A. Okay, so let's do that. So HA1 plus integral MA dt equals HA2. Okay, so the initial angular momentum is of course 0 because the spool is at rest. To find MA, we need to find external moment about A. The only force contributing to the moment is P. P times this distance, which is 0.9 minus 0.3. Is that right? Okay, so P times 0.6 tt, where t goes from 0 all the way to 4 seconds. What is the sign on that? Is it positive? It's negative, right? Because about point A, P applies a clockwise moment, so this is negative. Equals, okay, if you go back to the notes, I talked about formulas for finding HA. Okay, the formula which I told you was either you can use IG omega. Okay, that's if you find h about g, that's what you want to use. If you want to find h about any other point, then you can either use IG omega plus r cross mv. That's one option. But if you have rotation about a fixed axis, then you can use or if you have an IC, then you can use I about the IC times omega, right? So A is also the instantaneous center. Why? Because A is at rest as velocity of A is 0. So we could write HA as IC omega or I about A times omega. So A is going to be IG plus mass times this distance squared, 0.6 squared, times omega. Okay, I'm assuming omega is counterclockwise, which is positive. That's why I put a positive sign. But eventually, omega will come out to be negative, which means that the spool is spinning clockwise, which makes sense, right? Or does it not? It doesn't look like it's going to spin clockwise. It's going to be counterclockwise. No, it's going to spin clockwise. It looks non-intuitive, right? Friction force is that way. So velocity has to be this way. Friction opposes velocity of motion. Velocity has to be this way. If velocity is this way, then it has to spin clockwise, not counterclockwise.
I thought friction was spinning the wheel.
What's that?
Like if it's spinning counterclockwise, then friction would be to the left. And if it spins clockwise, then it would be to the right.
Friction opposes the linear speed, right?
Yeah.
If V is this way, then friction that way makes sense. If V is this way, the linear speed, then friction should be that way. So P is going to be, the other way to think about this is, if you do the linear F equals ma in this direction, x direction, P minus FF is going to be mass times acceleration. FF is usually small, so P is going to be greater than FF, so that is going to be positive. So acceleration is going to, the linear acceleration is going to be positive. And so it's going to move to the right. I trust the physics. It comes out to be negative. It seems counterintuitive, but I think it's right. It is going to spin clockwise, not counterclockwise. Just because the way P is set up. If you apply P too fast, remember there's a condition which is it rolls without slipping. Our experience is if you apply P too fast, then you have a tendency to go to the left, that is spin towards that way. But if you apply P in such a way that it rolls without slipping, then it will go clockwise, not counterclockwise.
But it won't spin.
It won't. It will spin.
I don't see how it doesn't move.
It spins because of friction. P is applied this way. The friction tends to cause it to spin. I think you can, if you do this experiment yourself, then it will actually go to the left because you will not apply P in the right way. That is, assuming spool rolls without slipping. Actually, I think what is very questionable is, will it actually roll without slipping? Under that assumption, it does do what it says it will do. But our experience has been, my experience would be we go to the left, not to the right. Okay, Ig is mass times k square. This comes out to be 5 lb times 0.6 times dt, which is 4 seconds, equals the mass, which is 30 divided by 32.2 times k square, which is 0.45 square, plus again mass times 0.6 square times omega. So we can solve for omega. This is negative 12.6 length per second. So another thing you can do is you can actually try to solve the same problem using F equals ma, using what you learned in chapter 2 chapters back, 17, and see if you get the same answer. Okay, if you do again ma equals I alpha, again ma is going to be r plus f, so ma is going to be clockwise, right? So alpha will be negative. If alpha is negative means it's going to spin clockwise. Its angular speed is going to be clockwise, not counterclockwise. If you try to do this, you get the same answer. Okay. Very counterintuitive. Next question. Okay, any questions on the previous question other than the sign? Yeah.
When you did the IA design for the M at 0.6 squared, how do you get 0.6?
It came from this. The inertia is about A. So, I think it needs to be this distance. My bad. Yeah, my bad. I wrote it incorrectly from my notes. It's 0.9 squared. Should be good catch. It's 0.9 squared. Should be this, because the parallel axis theorem, it says mg times the m times the distance from G to A. Good catch. So the answer is right because I have the same 0.9 in my notes. Any other questions? Okay, the 100-pound wheel has a radius of gyration of 0.75 feet. If the upper wire is subjected to a tension of 50 pounds, determine the velocity at the center of the wheel in 3 seconds, starting from rest. The coefficient of kinetic friction between the wheel and the surface is mu k equals 0.1. So velocity of the center of the wheel in 3 seconds. So velocity is a function of time, so you can use principle of a linear impulse or angular impulse. This one doesn't tell you to assume it rolls without slipping. Okay, so I'm going to draw the free body diagram first. So tension mg, normal force, okay, there's going to be some tension here. Let me call that R. Okay, and then I need to put a friction force. Okay, which direction should I put the friction? To the right or to the left? Actually, you can put it any way, either way you want. It'll actually come out with the right sign for rolling problems. Otherwise, in a normal case, don't put friction in the direction of velocity. In this case, it's okay to put in either direction. So let me put it this way, since this seems more likely. The velocity is to the left, the friction force should be to the right. Okay, the friction force is mu k times n, is mu k times mass times gravity. Okay, so let's see. So we want to find the speed as a function of time. Right? Now in this case, the previous case, we had the only unknown in that problem was the friction force. In this case, we have the friction force and R. Right? There are two unknowns. So if you try to do principle of angular impulse, the trick we used last time, we could use angular impulse here, 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 wherever you want. But if you use angular impulse about this point, R will appear. If you apply angular impulse about that point, F will appear. So it looks like we're stuck with one of the two, R or FF. So just using principle of angular impulse like the previous problem will not help us because there are two unknowns here. Okay, so you have to use the other equation, which is principle of linear impulse. So let's set that up and then apply the principle of angular impulse and momentum. So principle of linear impulse and momentum states that mass times velocity 1 plus the net force in the x direction, so that's going to be t minus hold on, my bad. I do know the friction force, right? Unlike the previous problem. So I do know, so writing this equation will not get me anywhere because if I write this equation, I have t minus r minus ff. So r is unknown. I'm not interested in knowing r because that doesn't help me. So my bad. I shouldn't set up the principle of linear impulse and momentum because I would have an unknown. So the way to do this is not apply linear impulse, but we use the principle of angular impulse and momentum about that point in which r would just disappear because you do not know r and you're not interested in solving for r. The place where you can apply principle of angular impulse and momentum is this point, right? Point A. If you apply point A, then r will disappear from the equation. So I would change this to angular impulse. Let's apply this about let's call this point A plus integral of the external torque m about A dt equals h A at 2. So we're going to assume that when the spool is unraveling from uh, uh, using the force T, there is no slipping taking place at A, which is a reasonable assumption. No slipping at A. Thus, velocity of A is 0. If the velocity of A is 0, point A is 0, then A is the IC. Okay? If A is the IC, that is simplify our life when we try to apply the principle of angular impulse and momentum, because that helps us to find HA. So proceeding with this, the initial angular impulse is 0. MA about A is going to be T times this distance, that's 1 feet. Okay, and the sign is positive because when T is applied, tends to spin the about point A. T applies a counterclockwise movement, so it's positive. FF applies a clockwise movement about A2. So F times this distance, which is going to be this distance is at 0.5. It's 0.5 times delta T, which is let me write it, delta T. HA is I A omega, which is also IC omega, right? Because A is the IC. So the tension is 50 pounds plus mu K is 0.1, mg is 100 times 0.5 times delta T is 3 seconds. IA is going to be the mass, which is 100 divided by 32.2 times the radius of gyration square, so 0.75 square, plus mass divided by 32.2 times the distance from this distance. D is 0.5. That's 50 plus that 5, right? Times 3 equals 100 divided by 32.2 0.7 square plus okay, what does that come to? Don't know, I did this math. Okay, 65. So omega comes out to be 65.39. Okay, so what's this? The solution saying is that speed is 65.39 in the counterclockwise direction. So velocity is to the left, right? Which makes sense. The friction force. Well, V is going to be, we asked for V, so I'm going to write V first. V is 65.39 times, it's going to be this distance, D, right? So 65.39 times D, or 65.39 times 0.5 equals 32.69, 32.7 radians per second. Because velocity, this point is at zero speed. So when I find the velocity, I need to use a relative velocity formula. Velocity of this point is velocity of the other point. It can be this point or this point, plus omega crossed with r. But I know the velocity of A, it is 0. I do not know the velocity of the point over here. I need to find that. So I just use the relative velocity formula. This comes from velocity of A plus omega crossed with V. This is 0. It's always when you find the velocity of G, let's call this G, you always use the formula relating the relative velocity formula. As long as you know the velocity of another point, you can use the formula. It's not random, it's just using that formula. If A, for most problems, A is the contact point of the spool with the ground, so we use the radius. So in this case, the contact point, well, not contact point, but the point with zero speed is A, not, let's call that C. It's not C. So omega is counterclockwise, velocity is to the left, right? Which means friction force is right. Friction force is to the right. It prevents. It basically is against the direction of motion. Okay, any questions?